Going at a 120-degree angle, is that right?
Yeah, away from point O, and then signal A moves at 14 knots, and should be moved at 21 knots. So one goes on the end of each arrow.
Okay.
That's
That's at 14 knots, is that right?
Yeah.
And the other one is moving at
21.
21 knots.
And then how fast are the ships moving apart when OA is 5 and OB is 3?
Yeah, I'm gonna circulate this.
How fast are they moving apart? So we kind of need a distance between them there. Anything you want to call that?
C.
X,
D for the distance.
D, C, it's Grace's problem, so it's X. So what we have here looks like a law of cosines to start with. So it's not a right triangle, so we can't just use Pythagorean theorem. All right. So we're gonna, and because OA and OB are kind of annoying, should we say that the side opposite angle A, should we call that side little a, and the side opposite angle B, we can call little b? It's kind of the traditional format. Is that okay?
Yeah.
So then we have, using our law of cosines, who could forget, x squared is a squared plus b squared minus 2ab cosine of 120 degrees.
Of course.
Of course. And so we know that A and B are changing with time, because as time goes, they're moving out this way. So that's going to make the x change with time as well. So everything's a function of time. Should we get, what is a cosine of 120? Negative 1/2, good, which is convenient, because then the negative 1/2 times the negative 2 cancels. So we're going to get x squared is a squared plus b squared. That'll be a plus ab. We okay to that? Let's see. We know that because we're going at 14 knots, and I don't know that it really much matters direction here. I don't think we have to worry too much about negative or positive. Well, negative would be shortening up. So the rate at which the side B is lengthening is, no, do we know? Oh, it's the 14 knots. Is that okay? So we know that dB dt is the 14, and the dA dt is the 21. And then we're interested at that particular moment when OA and OB are 3. I think we're going to have to come back to that because we're probably going to need to know what x is at that moment also, but we'll get there. Okay, so far. So now we're ready to actually differentiate with respect to t. So we're going to have some chain rules, and we're going to have a product rule in there. So the x squared is a chain rule, so that's going to be 2x to the first, and then times dx dt. All right, and then same way we'll get 2a to the first times dA dt plus 2b to the first times dB dt. And then we got a product rule. So we're going to get the first a times the derivative of the second dB dt plus the second b times the derivative of the first dA dt. So we got numbers for just about everything, except we're going to need to know what that x is. So I think we can come back to here, and using this OA is what we have actually called little b, and this OB, that length, is what we're calling little a. So we can, I'm going to come right here and say x squared is going to be the a squared, which is going to be 9, plus the b squared 25, plus a times b is 3 times 5 is 15. Oh, look at that. It's 49. Somebody really worked hard on this problem to get such nice numbers. Is that okay? So now let's see, we're looking for, what is it, we should say, what is it we're looking for? Yeah, we're looking for dx. Okay, so we have 2 times x, which we said was 7, times the dx dt that we're trying to find. It's 2 times a, which is 3, times dA dt is 21. 2 times b is 5, dB dt is 14. The a is 20, no, the a is 3, the dB is 14, b is 5, the dA dt is 21. All right, looks like 14 dx dt is 6 times 20 is 120, is 126, I think. 10 times 14 is 140. 30 plus 12 is 42. 105. Doing okay so far? Oh, you big cheat. Let's see, we've got 266, 268, 308, 408, 413. Does that sound right? Well, it was so nice up until now. So dx dt, 413 divided by 14, or whatever decimal you want for that. Does that sound good? Any other challenges for us here? So I allowed 2 days for related rates here, so we'll do some more related rates examples here, but maybe if we can steal away a little time, maybe we can come back and do some more optimization. I'm hearing that the optimization is a lot more challenging than the related rates. I think I perhaps not allow time in the right manner. Let's do this one. So kind of a different kind of problem. A point moves along the curve. Y equals 2x squared plus 1. In such a way that the y value is decreasing at a rate of 2 units per second. At what rate is x changing? At what rate is x changing when x equals 3/2? It's kind of a different kind of problem here. So we have we know what the graph of 2x squared plus 1 looks like. Roughly, that's a parabola that's going to open up. It's a little skinnier than an x squared parabola. It's going to have a y-intercept of 1. So what we're doing is we're imagining kind of some particle moving along this path. Okay, so it's because that point is changing with time. That's what we're saying here when it's increased, the y value is increasing at 2 units per second. So that must mean it's on this side of the parabola moving up. Okay, well, I don't want to take away any fun, so I'll let you take it away from there.
Sorry?
Hey, we can erase all that old stuff. So we can see we know the dy dt is -2, and we start with our y equals 2x squared plus 1. When we differentiate this with respect to time, I think this will actually be dy dt, and then a 4x times dx dt is good. We plug in what we know, solve for what we don't. I think we're agreeing on -1/3 units per second. Questions on that? Last minute editing there. It's okay. So let's, are we okay then if we switch over and do some optimization instead, maybe? Okay. Optimizations are harder. Want a picture of that, or can you figure it out? Picture? So we know that 1 minus x squared is going to be a parabola that opens down. It's going to have a vertex at 4, and we can see it's going to cross the x-axis at 2 and -2. So we're getting this parabola that's looking something like that. Now we're talking about a rectangle that is inscribed between the curve and the x-axis. We want to find the one that has largest area. All right. So let's just talk about this a little bit. And I want to see this on tape as too. So we did well. We got areas base times height, and we can see that this distance is x, which makes the base of the rectangle going to be 2x, and the height is going to be the 4 minus x squared. We found that we multiplied it out, we got the derivative. Now we got critical points at positive and negative square root of 4/3. Now it's worth, like we said, putting a little time and thought into restricting your domain as much as possible. Certainly we could say the domain goes from -2 to 2. But if you do that, then you're going to include both of these critical points. And now the argument for an absolute maximum becomes more complicated, because as you can see that the derivative is going to go negative, positive, negative. So even though square root of 4/3 is the only relative max, if the function is decreasing to the left of negative square root of 4/3, we don't really know without some more work, you know, if it's decreasing, is this relative maximum that we got at square root of 4/3, why do we think that that's bigger than some other point over here in between negative square root of 4/3 and -2? So there are kind of two ways you can go. If you stick with your domain being -2 to 2, then you're going to have to take the limit as x approaches -2 and show that that limit is less than the area that you get at the square root of 4/3, which isn't really hard because, if you look at this, as x goes to 0, this is going to approach 0. And that is, in fact, going to be less than the area we got when we plugged in square root of 4/3, which I think was, what did we say, 8/3?
Wait, I thought we were taking it as a approach -2.
It's 0 anyway.
Yeah, it's still going to be 0, sorry, because of the 4 minus
Yep,
x squared.
right.
Okay, yeah, good point. So we could say, that limit as x approaches -2, and we could even say it from the right, of our area function is going to be 0. So we're going to be okay. It just takes a little bit more doing. On the other hand, if you scratch your head a little bit and say, if these are the dimensions of our rectangle, then we really can't include negative values for x, because that would make for a negative base or a negative area, which isn't reasonable. So you can actually restrict your domain to be from 0 to 2. And if you do that, then your life becomes much easier, because now there's only one critical point on that domain. And now you can argue that because that's a relative maximum, because the derivative goes from positive to negative, and it's the only critical point, then that relative maximum, that we're seeing here, is the absolute maximum.
Is it reasonable to include that?
That's a bit of a philosophical question, and I think you could probably get away with it. It's a bit of a stretch maybe, but it would certainly make our life easier if we said it was the closed interval from 0 to 2, because then you'd get to use the candidate test and just plug in 0, plug in 2, and of course those are going to give you areas of 0, and then life is easy. It's a bit of a maybe stretch. I think you could probably get away with it here. I'm going to give you one in a moment where I don't think you can, and so then you're going to have to deal with this. How do we argue for an absolute max, absolute min, when it's an open interval? And I don't think that comes up very often on an AP exam question, very rarely, but it could. Much, much, much more often you're going to see a closed interval domain where they want to see the candidate test. The vast, vast majority of the time.
But if I use the other thing, are they going to dock me instead of the candidate test? If I do that instead?
This would still be acceptable.
So if we translated the graph to the left one, would we have to include a negative number in our domain?
I think that changes the problem entirely. Because now you don't have that symmetry around the y-axis. So, we've done a problem, I think, in the past, I don't know if you remember it, where we inscribed it in like the arch of a sine curve. And so now all of a sudden, because you're not symmetric around the y-axis, your dimension isn't going to be just a multiple of x.
Gotcha.
Okay. So like in this case, you'd get like, this would be x, and this would be like pi minus x.
Cool.
Okay, so there's symmetry, but not around the y-axis. Okay? All right, so let's change the problem here. It's going to look kind of similar, but instead of inscribing a rectangle, we're going to find the minimum distance to a point. So still we're going to use f of x equals x squared, but let's find the point. Find the point on F that is closest to, we'll say, the point 0, 2. So it's now a distance problem, not an area problem. Does that make sense?
Yeah.
So once you get to the place where you got your d equals the square root of, and it's all just x, the value of x that minimizes this whole thing is the same x that minimizes this without the radical. So your calculus gets easier if you just rename this and make that statement that the value of x that minimizes d hat is the same value of x that minimizes the square root of that. And now just do your calculus on the thing without the radical.
How do you, like, write that? Like, how do you show that the value that minimizes D is the same value that?
You don't have to show it. You can just state it.
We
So-
just say it.
I would just say the value of x that minimizes D is the same x that minimizes D hat. And then from that point on, you just work with D hat.
Yeah, but.
And just leave off the radical.
Leave off the radical.
Okay.
I can just
Is that
leave it off.
okay?
What is D hat? Is it
It's just, I just want to rename it so I don't have, I'm not talking about this D versus that D. So you've got, let me see if I can get caught up. So you've got, let's see, x squared plus, so x to the fourth minus, you've got x to the fourth minus 3x squared plus 4.
Yeah.
So D hat is going to be just leave off the radical.
Oh, so okay, that's good. I don't see the D squared, like D hat.
Yeah.
I don't see it.
Okay.
I need to.
So now you can take your derivative there. Well, we ran out of time.
Will we have more opportunities to work on things like that?
Yeah, you like doing this kind of stuff? Okay, we'll try to finish this up. What's that?
What do you think of the problem we tried to do?